Hey, what's up YouTube? It's SpeedoPlayer1011 here, and I have a different kind of video to show you today. So, in this video, we're going to be talking about a problem that I ran into when messing around with series, and I see a connection between e to the negative x squared and inverse tangent x that maybe someone can help me out with. Maybe something I didn't come up with myself, something someone else came up with it, someone knows, I don't know, we'll see. Anyway, so let me just take you through my thought process. We have e to the negative x squared, which is an interesting function because if you watched my Gauss's integral video, you'll know that the integral over the entire real plane is equal to radical pi. Anyway, so we have e to the negative x squared. We'll make e to the u an alternating series. So we're just going to take out the negative 1 when I write the actual thing from this. So this goes from n equals, it should be 0 in both of these. This is my mistake. So it'd be n to the 0 here, to infinity. And we take out the negative 1, so we have negative 1 to the n, because every odd term will be negative. And then we have x to the 2n over n factorial. And we know that, let's just take the integral of this to get the series expansion. I'm going to take this from negative infinity to infinity. Because we know what this answer is, it's radical pi. We proved this with polar coordinates, if you watched my last Gauss's integral video. So let's do that, but this time we'll take it with, we'll find the series expansion for this integral. So this is equal to radical pi. And when we take the integral of this, we notice something a little bit interesting, and I don't doubt that there is some sort of connection between this and inverse tangent. So, obviously you can just take the summation out, n equals 0 to infinity. We can take the negative 1 to the n out and n factorial out. So, we have negative 1 to the n over n factorial. Now, what we have left in the integral is x to the 2n, and this will be a very simple integral as we can just apply the power rule. So we have the integral of x to the 2n, and this is finally equal to, and you'll see that this ends up being a lot similar to this, and if most of you should already see this, as after we apply the power rule, we end up with 2n plus 1 in the numerator and 2n plus 1 in the denominator. Obviously, the 2n plus 1 in the numerator is the exponent to x. So we have n equals 0 to infinity, we have negative 1 to the n, x to the 2n plus 1. And now what I'm going to do is I'm going to separate this because this is kind of where my question ends up being. So we have 2n plus 1. And then we multiply this entire thing by 1 over n factorial because that's what that is. So we basically have a product here that is being summed. And we know that this is exactly what this is. And another thing to take note of is that inverse tangent evaluated from negative infinity to infinity. So I'm just going to put x here for the variable, and we're going to evaluate this from, oh, also since this is an integral, I should also put my bounds here too. So you have negative infinity to infinity. You have that here too. So you have negative infinity to positive infinity is actually equal to pi, because pi, inverse tangent of infinity is pi over 2. And then we subtract that from inverse tangent of negative infinity, which is negative pi over 2. And so this leads to something very interesting because we have that this evaluated from negative infinity to infinity is simply the square of this. And we know that the series expansion for this is contained in here. Now, I've been thinking a lot about this because I want to know if there's some way of splitting this up. And I recognize that the only way I know of that would maybe help is Lagrange's identity. And what that is, it's n equals 1 to infinity, and we have a n bn, and what he did was he squared it, and that was equal to something. I'm not going to write the entire thing out, but there are 3 problems with this that I saw. First is that I have bounds here, which means that I'm subtracting one from the other, and they're both infinity, so I have to take the limit approach in that, which makes very little sense in this case because I have a dummy variable as well as an x term in the numerator, whereas if I just plug in infinity, it would just be a non-real number, a concept more of anything. The second thing is that in this expansion, they still have these 2 terms put together. The advantage, though, also the third problem is that this is divided from n equals 0 to infinity, this is n equals 1 to infinity. Obviously, I can fix that just by making this n minus 1 and then these all 2n minus 1. However, that still doesn't get rid of the third problem. Why did I write n here? It should be squared. The next problem, which is that there's really no way to split these 2 up separately, because in the expansion that Lagrange came up with, we had these terms squared, and I don't want to mess up this identity right here, especially since if you square them, they end up with 2 totally different things, as well as subtracting from the integral of these 2 where they're still kind of combined. It's a double summation, and that identity kind of messes with the whole thing. So I recognize that this isn't something that can be expressed in elementary functions, but there's something with series that's connected here, and I want to know if there's a way of connecting the integral of e to the negative x squared with inverse tangent. Anyway, thank you for watching. I hope you found this little connection I found a bit interesting, or maybe you know about it already and want to help me out with it. So thank you for watching, and if you'd like to give me a thumbs up and subscribe. Thank you.